of identity attributes in the whole identity life cycle. So to this extent, I present privacy-preserving multi-factor verification of identity attributes. So this is a mouthful. What do I mean by this? By multi-factor verification, it means verifying that an individual owns an identity attribute by requiring proofs of ownership of other associated identifiers. To understand this, let's take a very simple example. If you go to a shop and you're trying to use a credit card, the shopkeeper may ask you for driver's license or some kind of photo ID associated, and they check if this is the same name and the same photograph and so on. So that is a multi-factor aspect. The second is the privacy preserving. So in the example I just gave you, the shopkeeper comes to see your driver's license, your age, maybe your state of residence and so on, which is not really required to verify that you own this credit card. So we want to preserve privacy, and therefore we use this concept of proof of identity, which is essentially a cryptographic token bound to the individual. And when it comes to identity attributes, we also consider various types of identity attributes, which is the biometric and the history-based. So very briefly, I'll go into the key main properties of the system. So we want some security properties, some privacy. We want the biometric and the history-based support. So we show what we really mean by these security and privacy properties in terms of some very basic properties of confidentiality, non-repudiation, and so on. These are some very strong properties that are needed in the system. And to achieve this, we have a framework which shows what are the key entities and how they interact in the whole life cycle. And then we have protocols to do zero-knowledge proofs used in the multi-factor verification, and then systems which show how to integrate the biometric and history-based identifiers for such multi-factor proofs. So just one slide on the framework. I don't go into the details on that, but the framework consists of three main entities. First is a principal, which is like any user using the system. For example, Homer07 is a principal who's using the system. Service provider is like eBay, Amazon, like any kind of service provider providing services. The registrars is a new type of entity, which is, I got a mail. So the idea is that these registrars establish and maintain identity commitments. So these commitments are there to are required to do zero-knowledge proofs, as we will see some examples. And now we just jump into the aggregate zero-knowledge proofs. The idea of these zero-knowledge proofs is to have a way to prove that you have multiple strong identifiers without revealing them in clear. Okay, so zero-knowledge proofs have been there for a long time, but the key aim over here is to provide mechanisms which are efficient and flexible for the purposes of multi-factor verification. So the tools that we use Peterson's commitments. So I'm not going into details. This would take forever to go into each one of them. But if you have any questions, let me know. Okay? So we use Peterson's commitments. The key thing to see here are those M and R in red. So the M is essentially the strong identifier, like the credit card number, your social security number. And R is a secret. R is a secret that is associated with the strong identifier in this particular commitment. And G and H are public parameters. So we also use bilinear maps in our protocols, which are actually used in Bonnet's aggregate signature. So the main idea over here is that multiple signatures can be aggregated into one signature, and it can be verified. Multiple signatures can be verified at once. And the basic zero-knowledge proof protocols we use is from Kamenisch and Stadler. We use their approach and even their notation. So here you see this fancy formula. All that it means is that the user is providing a proof of knowledge of two identifiers, alpha, beta. By Greek letters, we just identify those identifiers which are secret to the user, and which is of the form C equal to G to the alpha, H to the beta. So the key idea is that I can prove that I have alpha, beta without really revealing them in clear. Okay? Just to put it in perspective, like the registrar is the one which is storing what is called the identity record. So this identity record consists of commitments and commitments of the form which I just showed you, and the signature on these commitments. Note that the registrar never has the value of these strong identifiers in clear. It doesn't know the credit card number, it doesn't know the social security number, but they are just stored in this particular form so that the user can prove ownership of later. And also, along with these commitments is stored the assurance that I'm sure that this particular identifier is valid or not, that is validity assurance, and then the ownership assurance, which talks about how sure am I that you actually own this attribute that you're claiming. Okay? So let's look into some simple examples of how these zero-knowledge proof protocols are used. So I'll go through some instances. So here consider the case that Homer goes on to ask a service provider for a car insurance. Now, to get the car insurance, the service provider requests Homer for the clear values of the credit card number, the driver's license number, and the social security number. So Homer does not only want to provide these values in clear, he could potentially steal these values and provide it, right? So instead of just providing them in clear, he also wants to prove that he has the secrets R1, R2, and R3 associated with these strong identifiers. So he does some kind of an aggregation. He computes this aggregated signature and some other numbers used in the zero-knowledge proofs. Okay? So when he sends this in some token, so these are the commitments, the capital M1, M2, M3, along with the values of the strong identifiers, then they engage in a proof of knowledge. So in the proof of knowledge, he basically says that he provided these credit card number, driver's license number, social security number, but he also knows all the secrets associated with them. And remember, these secrets are never revealed in clear. Okay? But he can prove that he knows the bound secrets of each of these strong identifiers. So once he does that, the service provider can potentially verify the signature, the aggregate signature, and basically our techniques are very efficient. So you can just check one thing and you've checked the 3 strong identifiers that they requested. And if this signature is okay and the proof was okay, the Homer gets a service. So now let's consider another scenario where Homer is a Secret Service agent. Okay, so he has a reason to hide the kind of commitments that he has that he's enrolled. So and let's consider the government is the registrar. So if Homer has enrolled some commitments at the government, that means he's a government employee. So to request, while he's requesting for a hotel discount in step 1, the service provider says, okay, give me any 2 proofs that you have enrolled at the registrar. So at this point, Homer does not need to say that I enrolled my Secret Service agent number and something else, because just the fact that he enrolled those numbers reveals more information than that is needed. So what he does at this point, he just takes the signatures. He doesn't take the commitments, and he aggregates these various signatures in this particular manner. So he takes the cumulative signature of any 2 signatures and also prepares his secrets associated with those signatures. He sends this aggregated signature to the service provider, and now look what happens. In this particular proof of knowledge, not only is a verifier checking that the signatures are valid, but also that the person who is presenting it has all the secrets associated with it. So in this particular proof, in one step, he checks that he knows all the secrets associated with it, and each of these signature is from the government registrar. If all of this is correct, he gets a service. So to make this scenario even more interesting, let's consider the case when the service provider needs any proof that he has enrolled with the government. In this particular case, you have not only can Homer not provide a signature, he can provide a signature in a hidden form such that if he goes and proves the same thing to the service provider twice, these various things cannot be linked. So he stays unlinkable. So the first step is that he hides the signature. A very simple way to hide it, he just chooses a random and creates delta. Now, instead of sending the aggregate signature, he sends this delta to the service provider. And now the service provider and Homer engaged in this proof of knowledge, where he shows not only that the signatures is valid, but also he knows the secrets behind those signatures. So in between all of this, basically the key thing that we get is that that individuals can prove that they have certain strong identifiers